Hi children, good morning. In our previous class, we have discussed about Rutherford model and its drawbacks. The main drawback in the Rutherford model is when charged particles are rotating around the nucleus, also having positive charge, then the particles will get accelerated, so that their path will shrink and slowly the particles, electrons should fall into the nucleus and that atom should be destroyed. But it is not happening. Atoms are stable. So something wrong in the proposal given by the Rutherford. So to rectify it, again next Bohr conducted different experiments and he proposed some other way. See here also electrons revolving around the nucleus, but only in certain circular orbits, not as they like. Some paths are given, some circles are given around the nucleus. Only in those circular paths only electrons will rotate. In other places, the electrons cannot be rotated. These circular orbits are known as discrete orbits. Those circular orbits are known as discrete orbits. See here. Electrons are revolving only in certain circular orbits. These orbits, only electron may be here, or maybe here, maybe here, but not in between. So Bohr fixed the circular path where the electrons will present. Bohr fixed it. So these are known as discrete orbits, or these are known as energy levels, or these are also known as shells, another name, shells, discrete orbits, or energy levels, all these are. And they will be indicated with some more letters with K. First one is taken as K shell. First one, nucleus it is. The first one is named as K shell, indicated with first shell, N is equal to 1. The second one is L shell, N is equal to 2. Third one is M shell, N is equal to 3. Fourth one is N shell, N is equal to 4. So on. K, L, M, N, O, P, Q, like that you can continue. So Bohr fixed these paths. Electrons will present only in these paths, not in between the paths. As long as the electron revolves in these or shells, it does not lose energy. When electron present here, it does not lose any energy. He fixed it. He calculated the energy also. In your higher class you will learn it. Energy is emitted or absorbed. Energy may be given out or may be absorbed when electron is moving from one orbit to the other one, from here to here, or from here to here, or from here to here. If they are coming or moving within the shells, then only energy changes will occur. Otherwise, there is no change in their energies. With a fixed amount of energy, they will continue their rotation around the circular path in the nucleus. The energies of these discrete orbits are fixed. Hence, these are also called stationary states or energy levels or shells. Indicated with K element or N is equal to 1, 2, 3, 4. Electrons will present only in that one. Next, and also by using various rules, we can fix the number of electrons also. The maximum number of electrons present in a shell is given by a formula 2n square. The maximum number of electrons present in the shell is given by the formula 2n square, where n is the shell number. If it is first shell, n is equal to 1, 1 square, 1, 1 into 2, 2. So in first shell, only you have 2 electrons. See, in the first shell, when k is equal to k shell, when n is equal to 1, 2 into 1 square, only 2 electrons you can accommodate in the first one. Similarly, in the second shell, 2 into 2 square, 8 electrons. Third shell, 2 into 3 square, n is equal to 3, 8 electrons. In third shell, you can accommodate 18 electrons. In fourth shell, you can accommodate 32 electrons, and so on. So, by using 2n square formula, how many electrons you can keep in those, accommodate in those shells, you can fix it. Not more than this, but less may be possible, but not more than electrons you cannot arrange in those orbits. And extra, in addition to that, the maximum number of electrons that can be accommodated in the outermost orbit, last one should not contain 8. though its capacity may be 30, 32 or 100 what it may be, but if it is the last one, we cannot give more than 8 electrons there. Maximum capacity is 8 if it is the last shell, first condition. Electrons are not accommodated in a given shell unless the inner shells are filled. First inside shells should be filled, then only you have to go to the higher levels. That is only based on some certain rules again. That we will discuss later, not now. See now, based on that, the arrangement if you observe, first one is here boron. Boron is a nucleus. It is nucleus. Boron is having 5 electrons. So 2 in the first shell, 2 in the first shell, and 3 in the, because first shell capacity is only 2. We cannot arrange more than 2 over. And next shell capacity is 8. Next second shell capacity is 8. But you have only 3 electrons, so 1, 2, 3 is given. Carbon, there are 6 protons, 6 electrons. See, 2 capacity first shell, remaining 4 are here. To take aluminium, total number of electrons are 13. 2 in the first shell, 8 capacity in the second shell, 8, and the last shell, the remaining 2 plus 8, 10 are arranged out of 13. The remaining 3 are in the third shell. First shell is K with 2 electrons. Second shell is L shell with 8 electrons, and third shell is M shell with 3 electrons. 2, 8, 3 for aluminum. The same way the remaining also you can arrange up to 8 electrons. You can practice it. See, hydrogen, helium, lithium, and atomic number means number of protons. How many protons are there? That is fixed. If protons changes, element also will change. 1 proton, hydrogen. 2 protons, helium. 3 protons, lithium. If proton changes, element also will change. These are the symbols you have studied already in the previous class. So symbols and atomic number equal to protons. And neutrons may vary. This is depending on the atoms. Electrons, if atom is neutral, same number of electrons, 1 proton, 1 electron. 2 protons, 2 electrons. 3 protons, 3 electrons. How they are arranged? In first shell, K shell, only 1 electron in the case of hydrogen. In the case of helium, 2 electrons, because K shell is 2, capacity 2 are here. Next, lithium, total 3 electrons. So out of 3, K shell capacity is only 2 and L shell capacity is 1, 2, 1. So if you go for sodium, 11 electrons, first shell capacity is 2, K, next shell capacity 8, next shell capacity is 1, only the remaining 1 electron only, 2, 8, 1, 11 electrons. This valency is, I will tell you later. Valency. What is valency? Valency is nothing but the combining capacity of the atom. Combining with how many atoms it can combine or how many bonds it can make, that can be taken as valency. And valency shell. This last shell will be the valency shell. Here for this atom it is only the last shell. But here, from here onwards, lithium onwards, L shell is the last shell. From here onwards, sodium onwards, M shell is the last shell. So the last shell will be named as valency shell. The electrons present in the shell, last shell, are known as valency electrons. Electrons present in the last shell are known as valency electrons. Here, the valency electrons only 1 for sodium. For magnesium, valency electrons are 2. For aluminum, valency electrons are 3. Whereas here, Again, valence electron 1, because it is the last shell for these are the valence electrons. This is the last shell, only one shell, these are the valence electrons. So last shell is named as valence shell. The electrons present in the valence shell can be taken as valency electrons. Whereas valency is different. Valence is with how many atoms it can combine, how many bonds it can form, can be taken as its valency. Hydrogen, valence is 1 means it can make only one bond. Helium, the shell is completed, no gap in this. So it cannot make any bonds with any other atoms, already completed. So valence is 0. You also see 8. The L shell capacity is 8, fully filled. So it can also cannot combine with any other atom, 0. And the remaining, you can combine with one atom, you can combine with 2, you can combine with 3, like that you are getting. With how many atoms it can combine, can be taken as valency. But here you have to remember one formula. Generally, why they are combining? To get stability. When they will get stability? If the last is containing 8 electrons, stable, it cannot react. Or if it is equal to the helium configuration, also cannot make. So all other things, either to get 8 or to get 2 nearby hydrogen. In such a case, they cannot combine. So here see, suppose we take this one 7, valency. To become 8, 1 is less. So it will make only one bond. Valence is 1. 6. To make 8, because it is a stable one. To get 8, it requires 2 electrons. So valency 2. Come here, 1. To get 8 or to make 2, it loses this electron to get 2, so its valence is also 1. So to get either 2 in the case of nearby helium, or in other cases to get 8. Here is also see 8, last is containing 8. So where if it is containing 8, no bonds, means stable. All other atoms nearby that one will try to get. So either 1, 2, 3, 4, or again 3 to 1 means maximum valence is only 4. Maximum valence is only 4. So if valence shell is containing up to 4, either 1, 2, 3, 4, their valency is also same number 1, 2, 3, 4. If the valence shell is containing more than 4 electrons, then 8 minus that number. 5 electrons are there, 8 minus 5, 3. 6 are there, 8 minus 6, 2. 7 are there, 8 minus 7, 1. Like that, we can calculate the valency. If the valence electrons are up to 4, same number can be taken as valency, because the same number of electrons can combine. If valence electrons are more than 4, but it cannot be more than 8, because one rule is there. Maximum should be 8 in the last shell. If more than 4, then 8 minus that number can be taken as valency. You can find out the valency of various elements. This is the last table. Here this is an exception. This will be there in your higher classes. Next, atomic number. Atomic number is nothing but number of protons. How many protons are there? That can be taken as atomic number. Hydrogen having 1 proton, so atomic number is 1. Helium having 2 protons, atomic number 2. Lithium having 3 protons, atomic number 3. So on. Number of protons. Next, mass number. It is nothing but sum of protons and neutrons. Sum of protons and neutrons can be taken as the mass number. See, carbon having 6 protons and 6 neutrons, so mass number is 12 units. Do atomic mass units, you might have studied in your previous class. Aluminium having 13 protons and 14 neutrons, total 27 units is the mass of the aluminium atom. Mass number is nothing but protons plus neutrons. See how to indicate it. This is the element. Atomic protons here, right here, atomic number. Mass number here, write it. See, carbon, element name 6, atomic number 12, mass number. Either you can write this side or you can write this side. Your textbook follows this method, you can write here 12 and 6. So the top value will indicate the mass number. This value indicates the protons. See, 12 is the mass number. Out of that 12, 6 are protons. The remaining are neutrons. 12 minus 6 are the neutrons. And the next one is isotopes and isobars. Two things you have to learn: isotopes and isobars. Isotopes are the atoms having same atomic number but mass number is different. Remember, isotopes are the particles which are having same atomic number but mass number is different. See, hydrogen, one atomic number, hydrogen having one atomic number, hydrogen having one atomic number. Atomic number is same, but masses are different. 1, 2, 3. Why the masses are different? Because of the presence of neutrons. Here 1 minus 1, 0 neutrons. 2 minus 1, 1 neutron. 3 minus 1, 2 neutrons. So because of the different neutrons, you are having different types of particles. But having the same atomic number, element cannot be changed. Same element, same properties. Physical properties may be different, but chemical properties will be same because element is same. Why element is same? Because proton number is same, atomic number is same. So these are isotopes of the hydrogen. First one is named as protium. This one is named as deuterium. This one is named as tritium. The names of hydrogen isotopes are protium, deuterium and tritium. Whereas the carbon isotopes, two are given here. Carbon 6 atomic number, carbon 6 atomic number, but mass number is 12 here, 40 here. So these two are isotopes of the carbon. Similarly here also isotopes of the chlorine. Where the atomic number is same but mass numbers are different, they are known as isotopes. Be careful. Atomic number same. So when atomic number is same, atoms are same. When atoms are same, chemical properties are same, but little bit physical properties may be different. What are the uses of isotopes? In your textbook, 3 uses are given. Uranium isotope can be used in the nuclear reactors. Cobalt isotope can be used to treatment of cancer. Iodine isotope can be used in the treatment of goiter. 3 are given in your textbook. You can by heart it and you can utilize. Isobars. Here mass number is same, atomic number is different. See here, mass number is same, atomic number. Calcium 20 atomic number, mass number is 40. Argon, atomic number is 18, whereas mass number is 40. Here mass number is 40, here mass number is 40. Whereas atomic number is different, 20 and 18. Because protons are different, 20 and 18, elements are also different. This is calcium, this is argon. Elements, protons are different means elements also differ, so their chemical properties are also different. Here atomic number is different, whereas mass number is same. Such a case we can call them as isobars.